Okay, in the last video we talked about how our usual equation for the force of gravity is only an approximation when we know the value of g, the gravitational acceleration or the gravitational field strength, and that Newton's universal law is exactly that. It's universal. I can use it anywhere in the universe. This only works where I know the value of g and where the value of g is going to be constant. That's also true for our equation for energy. We have gravitational potential energy is mgh. Again, this equation is only useful when g is constant. When we start talking about moving objects large distances, like putting something in orbit from the surface of the Earth, suddenly g is not always going to be 9.8 as we get higher and higher. So we need to find a new equation for gravitational potential energy. So here's a simplified version of the Earth and an object on the Earth, obviously oversized object on the Earth. But we're going to take this object and we're going to move it from the surface of the Earth out to here. So in order to lift it this distance, d, we're going to have to do work. We're going to have to change the energy of this object. Okay? So in order to change the energy, we have to exert a force over that distance. Okay? Work equals force times distance. Now, the force that we're going to exert, obviously, is Newton's universal law of gravity, g times m1 times m2 over r squared. And then we're going to multiply that by d. Okay, so g times m1 times m2 over r squared times d. Now really, r and d, other than the radius of the Earth, are relatively the same. Okay, so we can cancel one of them. And what we have is a new equation which tells me the work. And we know that work equals change in energy. So the change in energy of this object is going to be the final minus the initial change in any quantity is final minus initial. So we would have, let me write it down here maybe, g times m1 times m2 over r final minus g times m1 m2 over r initial. Now there's only one problem. If you look at the formula sheet, there is a negative sign on this equation. So that means down here we'd have a negative sign and another negative sign. That's going to complicate things. But where does this negative sign come from? Why would energy be negative? Well, we have to think about it as, we know that when we're lifting this object from the surface of the Earth outwards, we're increasing energy. Right? We know that when we lift something, I'm adding potential energy to it. But what if I took the separation between these two and made it infinity? If I took this object and moved it as far away from the Earth as possible, how much potential would there be for it to get pulled back by the Earth? Well, at infinity, it makes sense that the potential energy has to be zero. So how can I be increasing the energy, but increasing it towards zero? Well, that's where the negative sign comes in. If the energy itself was initially negative, and we plotted energy on the y-axis and separation on the x-axis, we can increase the energy as we increase r, but it would get closer and closer to zero as r gets closer and closer to infinity. So the energy is increasing, but it's increasing from a negative value up towards zero. So gravitational potential energy is a negative energy. Okay, so our equation now for potential energy, negative G times M1 times M2 over R. Often we'll refer to this type of energy as being bound in the Earth's gravitational well. And if you looked at modern theories of gravity where the mass of the Earth is actually bending the fabric of space as well, making it look as if it was a well, like that you're falling down into the Earth. This negative sign indicates being trapped in that gravitational well. Okay, so again, we now have two equations for calculating potential energy. The first equation, the one that we looked at previously, is useful when you know the value of G, and the value of G is going to be constant. And now we have another equation which is more universal. So as long as we're lifting, say, a relatively small distance, like say 100 meters, these two equations should give us the same result. So down here, suppose we're lifting a 10 kilogram mass from the surface of the Earth, so in a gravitational field of 9.80, and we're lifting it 100 meters. We say that we're giving that mass 9,800 joules of potential energy. So I've increased the energy. Okay, so again, this is the increase in energy. If I do the same calculation over here, I'll get the same result. So again, this time we're trying to find the increase in energy. So what we're really looking for is the change in energy, which is what this equation also tells us. It tells us the change in energy when I lift it that distance 100 meters. So again, we're looking for final minus the initial. So the final, negative G M1 M2 over the final separation, minus, and then I have another minus for the energy, so it's going to become plus the initial. Now, the G, M1, M2 is common, so I'm going to factor that out. And then I'm going to rearrange this so that it's a little bit more useful. So I don't have a negative at the beginning. So I've taken this, which is positive, and just moved it. So I have G times M1 times M2, the initial radius minus the final radius. That would tell me the change in energy. So I'm going to move down here and start writing this out. G is a constant, which we know. M1 is our 10 kilogram mass. M2 is the mass of the Earth. And then I'm going from the initial radius, which was basically I'm at the surface of the Earth. So the radius of the Earth and then I'm going to subtract the new separation, which is the radius of the Earth plus the 100 meters. And what you find out is we get almost exactly the same answer. We're different by 1 joule. So you can see the two equations give us the same result.